Welcome everyone to Digital series on FluidSIM. This is the third video in which I'm going to actually discuss actuators and provide further information about single acting cylinder and double acting cylinder. If you have already watched the second video, we have covered basically a single acting cylinder and double acting cylinder and provided three different examples in which we could control the motion of single acting cylinder and double acting cylinder with the use of different combination of directional control valve. In this lab and basically in this video, my aim is to cover a bit of theory about the single acting cylinder and double acting cylinder, and also show you guys another example in which we can see further details of single and double acting cylinder. Okay, so one of the important component in pneumatic system, as I said before, is actuators. And what actuator does, basically an actuator is an output device for the conversion of supply energy to the useful work. So how we basically can trigger the output signal is triggered by the control system, and the actuator responds to that command signals via the control element. So we have the signaling elements, we have the controlling element, and at the end we have basically the actuators. So we have different forms of actuators, and we can divide it in two different groups. One of them is going to be the linear motion and the other one is the rotary motion. So the focus of these videos basically in these series mainly is single and double acting cylinder. So what is single acting cylinder? We already saw how the single acting cylinder works inside the FluidSIM, and also we covered a bit basically the application of single acting cylinder. So when we talk about single acting cylinder, we are going to provide the compressed air, and that compressed air is going to be basically provided from one side of the piston surface, and the other side is open to the atmosphere. So the cylinder can basically produce the work only in one direction. So the return motion that we have for the piston is going to be caused by the built-in spring that we have inside the single acting cylinder, and it's going to apply the external force, or let's say the force needed for retraction. So the force, the spring force of the built-in spring is designed in general to return the piston to its start position, and we generally call that position the fully retracted position. Okay, so here we can see the single acting cylinder, and this video is basically showing how the fluid is going to be basically provided for the single acting cylinder from one side, and when that fluid is going to provide enough amount of force, that force is going to basically overcome the spring force, and from there we would have the motion towards fully extended position. Let's see this here. As you can see, this is basically here you see the fluid is coming. Let's say in pneumatic system we would have air. The air would come inside, right, and that air would overcome the spring force, and once that spring force is fully basically overcome there, right, we will have the air which is pushing this basically piston towards fully extended position, and then once that air, let's say the directional control valve is not sending the air anymore, right, the spring will push this piston towards the fully retracted position. Here we can see one of the commercially available single acting cylinder. So in general, the extending speed and the retracting speed of the cylinder are different. So Another important thing is usually single acting cylinder are designed so that the extending speed is greater than the retracting speed. And as you know, as I discussed in previous lab and also in here, work is carried on one direction. Okay, so we just have the work in one direction. So why we use a single acting cylinder? There are many reasons behind it. The construction and simplicity of operations make the basically single acting cylinder very useful for the following applications. For example, for transferring, clamping, branching, lifting, converging, and let's say allocating. The other form of pneumatic actuators that we have is called double acting cylinder. So the construction principle of a double acting cylinder is like that of the single acting cylinder, although we don't have any sort of return spring, and the two ports are used basically for the supply, right? So we have one of them for the supply and the other one, for the exhaust. So we have a supply part which is going to provide the air from the pump, right? And the other one is going to be basically the exhaust, which is going to be connected to the exhaust. Advantage of double acting cylinder is that the cylinder can carry out the work in both directions, right? In this specific case, we can have the work in both directions, but in single acting cylinder, we just have work in one direction. So as you see in here, so first we have the air from like the pump side, right? And then we have the air from the other side, and this is going to basically in the form of extension and retraction for this specific sort of actuator. See here? Okay. One question is how we basically can find the piston force in single acting cylinder and double acting cylinder. Before that, we have to look at the performance characteristic of cylinder, right? They can be calculated with basically theoretical formulation or with the help of the manufacturer's data. So both of these methods are possible, but in general, we mainly rely on manufacturer's data when we are dealing with an industrial application, or we are dealing with a specific version of a specific or let's say certain applications. So what is the piston force? When we are talking about piston force in single acting cylinder or double acting cylinder, we are basically looking at the pressure, right, and the amount of pressure which is going to be applied on the piston head, right? So easily we can say that theoretical force is going to be equivalent to the area and then times the pressure that we have on that area, right? So what is that A? Basically the usable piston area, and the pressure P is going to be the working pressure which is coming through the directional control valve to that single or double acting cylinder. So in practice, the effective piston force is important. We are not dealing with theoretical force, we are basically dealing with practical force available, right? So when we are calculating the force, we have to consider the frictional resistance over there, right? Without considering that value of the friction which is happening over there, we are basically calculating the incorrect value of force. So under normal operating conditions, pressure range is about 400 to 800 kilopascal. So the friction force can be assumed to be about 10% of the theoretical force that we can usually calculate based on the equation that we have in here. Okay, so for single acting cylinder, we would have, because one side is going to be the spring force, right? The other side is going to be basically the force that we are going to apply based on the pressure, and also we have the friction force over there. So the effective force is going to be the pressure times the area minus the returning spring force minus the friction force that we have. But For the double acting cylinder, the scenario is different because we don't have any sort of a spring over there. So the force that we are going to calculate is going to be different from forward stroke or the return stroke, right? So for the forward stroke, we would have the effective force equal to the area times the pressure, and it is going to be subtracted from the friction force that we have, right? From there we can find the effective force, and the return stroke is going to be A prime times P minus the friction force. And what is the difference between this 2A prime and A? You can see in here, which is basically the useful piston area. So when we are talking about the forward stroke, we are dealing with the total area that we have for the head of piston, which is going to be equivalent to pi d squared over 4. But when we are dealing with the return stroke, we would have the area of the piston, right, and the rod connected to it. Therefore the A prime is going to be equivalent pi times d squared minus the lowercase with d, which is basically the diameter of the rod connected to that piston, over 4. So the effective force that we have for the forward stroke and the return stroke is going to be different. Okay, that is basically the introduction, let's say, on theory behind the single acting cylinder and double acting cylinder, and how in general we can calculate the value of forces in let's say in the forward stroke or return stroke. In the second part of this video, I'm going to show again another example related to the single acting and double acting cylinder, and provide further details in FluidSIM and how we can basically play with different parameters inside double acting cylinder and single acting cylinder in FluidSIM. Okay, we already discussed about the differences that we have between single acting cylinder and double acting cylinder. In this part of the video, I'm going to do some experiments, and also we'll look at the properties that we have inside the single acting cylinder and double acting cylinder, and basically how we can configure a single acting cylinder or a double acting cylinder for a certain application. As you see in the left side, we have a very simple pneumatic circuit in which we have the air supply, air service unit, a directional control valve in which we have basically a form of manual actuation, and a spring return with 3 ways and 2 positions basically. And here we have the single acting cylinder. On the right side, we basically have the same sort of pneumatic circuit, but instead of having single acting cylinder, we have a double acting cylinder, and here we have a directional control valve with 5 ways and again with 2 positions. So the aim in here is to look at the properties that we have inside the single acting cylinder and double acting cylinder, and how we basically can adjust them. So let me look at the single acting cylinder here. So what we have, as you see, we have 6 different tabs, right? So the first one is called component parameters. We have drawing properties, configure cylinder, actuating, labels, force profile, and external load. In general, the important tabs in here are component parameters, configure cylinder, actuating, labels. In most of the cases, we use these 3 tabs. So what we have inside component parameters, you see we have piston diameter, piston rod diameter, piston position, maximum stroke, and mounting angle. So what you can observe in here, in the theoretical side, we already discussed how we can calculate the force, right? And when we were calculating the force, the parameter needed over there was basically the diameter that we have for the piston, right? And the piston rod diameter was also important for us. So what we have in here are the information needed for calculating that force, and the software is using those informations. And we basically can adjust the parameters depending on the application that we are working on. The other thing that we have in here is the piston area. If we already have the diameter over there, basically the software internally is going to calculate those values for us, right? And you see we have the display item in here, which means whenever if you want to see that item, that parameter inside the simulation, we can just check this and we see the parameter over there. And the other thing we have in here is the position, velocity, acceleration, force, and physical spring force. Basically, if we check each of these display items, we can see the value of each of these parameters inside the simulation. The good point in here is we have a good visualization out of these parameters, and in case, for example, if we are controlling the velocity of the actuators, we can easily observe what is going on there. So that is related to the component parameters. The other thing is drawing properties. We can adjust basically the shape that we have, the size that we have for the single acting cylinder, and it is the same for double acting cylinder. Basically the component parameters is going to be the same too. The other thing is configure cylinder. You see in here we have single acting, two form. One of them is going to be from the basically the fully advanced position, and the first one is basically starting from the fully retracted position. And we have the return spring. It can be basically located in the left side or the right side. We have cushioning. So what is the cushioning? Basically, you see we have the piston inside, right, and that piston is moving inside a housing. Whenever it reaches to the fully advanced position or fully retracted position, there is going to be an impact between the rod and the housing, right, between the piston and the housing. We need to have a sort of cushioning in order to avoid that impact and to have a safe motion inside that housing. So that's why we need to have cushioning. And sometimes we need to have adjustable, right, and in some industrial applications we need to have self-adjusting cushioning. So the good point about having adjustable cushioning is because we have that basically sort of cushioning inside, it is possible to have some sort of oscillation. And if we have the capability of basically cushioning, we can reduce the amount of oscillation happening over there. So that is one of the advantages that we have. And here we are getting that basically features in order to mimic the real world industrial applications. And another thing that you can see in here is the piston position. Basically we can adjust the position of piston in here and moving it like in the middle, or it can go even all the way to the basically the fully advanced positions. The other important point is the piston rod. So we can have different form, different shape for the piston rod based on the application and based on, let's say, the practice that we are working on, the industrial practice that we are working on. So another important thing we have in here, we can put the name, like let's say description, and we can have the identification, which is very important. Any circuit that you are designing, you have to put the labels for each of the components in there, because it is going to make reading of that circuit easier for the technician who is working on that specific circuit. We have actuating labels. So what is actuating labels? Basically with the actuating labels we can link the motion of single acting cylinder, or let's say the actuator, with the directional control valve that we have. So let's say we have a sort of mechanical motion and mechanical actuation for the actuator, right? With this linking and basically sensing the position that we have for the rod inside the housing of this single acting cylinder, we can actuate the directional control valve, and from there we can have the next step of the motion. So in the course that we are like in near future we are going to look at displacement step diagram, and over there we will see how we basically can connect the motion of single acting cylinder and the position of the piston to different steps and the sequences for a certain industrial application. And let's say we have an electro-pneumatic circuit right over there with linking of this, basically the position of piston inside the housing. We can have the actuation for the solenoid or relay connected to that specific solenoid that we have. And here we can have, basically we can define the force profile for the motion in here. So we can define a force profile, and based on that we can have a certain motion for the single acting cylinder and adjustment accordingly. And this is the external load. We can basically have a sort of static friction or sliding friction coefficient, and even we basically can choose certain material. Again, it depends on the application that we are looking on it. Okay, so these are all different tabs that we have for single acting cylinder, and we can play with each of these basically tabs and the parameters over there to get basically the sort of behavior that we expect, and also mimic what we are designing in a certain application. Okay, so that is the single acting cylinder. If you look at the double acting cylinder, in terms of basically the symbol, it's different. As we already discussed, we don't have any sort of spring, and here everything is going to work based on, if we're looking at a pneumatic circuit, everything is going to be based on air coming from one side and basically coming from both sides, right, instead of that spring. So if we look in here, you see everything is going to be almost the same, right? We have the maximum stroke here, so which means how much we can move, we can travel inside the housing, and the piston can move over there, right? And then we have, you see, we have all those simulated values, as you see in here, the position, velocity, acceleration, force. But here we don't have any sort of a spring, therefore the physical spring force, if we display it, is going to be 0 for this certain application. Similarly, we have the drawing properties, configure cylinder, actuating labels, right? The same sort of cushioning as you see in here, we already have that cushioning. Actuating labels, we already discussed how it is going to work, and we will see lots of examples. Specifically when we reach to the part of displacement step diagram, we'll see how we can link the position of piston inside double acting, or let's say single acting cylinder, to the actuation mechanism for a directional control valve, and from there we can have sequences. Here we have the force profile, already discussed how it works, and we have the external load, which is going to be the friction, and we already discussed how friction can impact the theoretical force values that we can get out of the single acting or double acting cylinder, and we can get basically the actual force out of it. So this is basically the properties that we can see for single acting and double acting cylinder, and as I said, based on the applications that we are dealing with, we can adjust each of these parameters. In the next video, I will focus on basically directional control valve and how we can adjust directional control valve and the parameters that we have for each of them inside the FluidSIM, and basically the meaning behind each of the symbol that we have for the form of actuations, and from there we will be completely ready for designing advanced circuits. Thank you very much for watching this video. Hope you enjoyed. If you enjoyed, please subscribe our channel.